Hi, I'm going to present our project, GenTree, using decision trees to learn interactions for configurable software. Modern software systems are increasingly designed to be highly configurable, which increases flexibility but can make programs harder to develop, test, and analyze. Our work focuses on answering the questions: how are config options set to reach certain locations, and what characterizes the config space of an interesting or buggy program behavior. We introduce GenTree, a new dynamic analysis that automatically learns a program's interactions, which are logical formulae describing how config options map to code coverage. For example, here, the logical formula x and not y or z equals 2 is the interaction for L1 and L2, because whenever it's true, then L1 and L2 are covered. GenTree uses an iterative refinement approach that runs the program under a small sample of initial configs to obtain coverage, then build decision trees representing interaction candidates. Then analyze the trees to generate new counterexample configs to further refine the trees and interactions in the next iteration. We'll show how GenTree works by using a C program with 9 locations L0 to L8 annotated with their interactions. For example, L0 is covered by every config, and L8 is covered by any configs in which S is false, E equals 2, and exactly one of U or V is true. The config space has 3,888 configs. GenTree first create a random one-way covering array to obtain a set of initial configs. Then for each location L, we use the C5I classification algorithm developed specifically for this work to build a decision tree representing the interaction for L. Here we show the decision tree for L8, which says that when S is false, L8 is hit, and when S is true, L8 is missed. Hence, the interaction represented by the tree is not S. This is quite different than the desired interaction for L8, but is still partially correct because not S is part of the requirements for hitting L8. Then, for each location, GenTree generates new counterexample configs to refine the tree. We prioritize paths with less boring configs. Here we choose the path A and generate new configs all having S be false. If the tree is correct, then L8 should be covered by all newly generated configs. But C4, 5, and 6 don't cover L8. We found 3 counterexamples. So we rebuild the decision tree for L8. Our candidate interaction is converging to the ground truth now. Then we repeat the process of building trees and generating new counterexamples until we cannot find new coverage or refine existing trees for several consecutive iterations. At the third iteration, GenTree creates 9 new configs and found 4 counterexamples. The candidate interaction now matches the ground truth, and GenTree will stop after some more iterations because the tree for L8 won't be changed anymore. In the post-processing step, for each location, we combine the hit path conditions of the tree into a logical formula. In a complete run, GenTree found correct interactions for all 9 locations L0 to L8 using around 360 configs out of 3,888 possible configs in under a second. Most decision tree classifiers employ pruning strategies to simplify trees and need large datasets to produce accurate results. We developed a simplified version of C5.0 called C5I for interaction learning. It has no pruning and hence 100% accuracy on the training data, but the tree may be overfitted. GenTree iterative refinement phase is designed to mitigate this problem by generating counterexample configs to gradually correct overfitting mistakes. We evaluated GenTree on 17 subject params spanning 4 languages, with config space ranging from 1,000 to 100 trillion configs. We did 4 experiments on accuracy, performance, interaction analysis, and comparing with iGen. GenTree results are highly accurate comparing to the ground truth interactions found by exhaustive search. GenTree can infer the exact interactions for most test params. GenTree also scales well to large params because it only explores a small portion of the config space. For example, ls has the config space of 10 to the 14th, but GenTree only uses around 100,000 of them. GenTree can quickly converge to the exact interactions. At around 40% configs, GenTree infers more than 90% exact interactions, and spends the rest of time refining few remaining difficult interactions. The counterexample generation heuristic helps GenTree outperform the random version and stays dominated throughout the runs. We analyze the discovered interactions to learn interesting properties in configurable software. Our results are consistent with the observation made in previous interaction works like i3 and iGen. The singular and conjunctive interaction forms are common, but disjunctive ones are rare. Mixed interactions are common in more complex params. The number of obtained interactions is far fewer than the number of possible interactions, and they are relatively short regardless of the config space size. Enabling options are common and can be found in most params. And one useful application of GenTree is using the inferred interactions to compute a minimal set of configs with high coverage. For example, we only need 18 out of 6 billion configs to cover 1,085 lines in sorts. Comparing to iGen, GenTree explores more configs, but also discovers more expressive interactions. For example, for sorts, iGen fails 122 mixed interactions, while GenTree fails only 2. In conclusion, we present GenTree, a new dynamic analysis for interaction learning. By using decision trees, GenTree supports expressive interactions represented by arbitrary Boolean formulae and allow for generating effective counterexamples. By using a custom classification algorithm, GenTree can build trees from small data samples. We work on integrating iGen pure formula inference algorithm to reduce the number of configs used, applying fuzzing and genetic techniques to get better initial traces, and adapting GenTree to different domains, like for learning activation patterns in deep neural network. The implementation and evaluation data are available on GitHub. Thank you for listening.
Okay, good morning, good evening, good night. Welcome again to this session called Testing General Issues. Let's talk about the second paper of the session, that is GenTree, using decision trees to learn interactions for configurable software. And I am glad to present the authors, Kim Howard and Nguyen, and Tambu and Nguyen as well. They are so eager to reply to your questions. Let me check the chat. So no questions so far. No problem, I have some. Well, first of all, I would like to congratulate you for the work done. It's a very interesting proposal because I think that taking into account how different configurations, option settings map to code coverage, it's a good idea. It's quite valuable, especially taking into account that current application or today's application are very configurable. So it is a problem that it's quite common, let's say. So I saw from the paper that your results are promising, that you did this feasibility study, 17 programs. And based on your results, I mean, you have a very promising, as I said, results. So I would like to know what kind of systems do you have a clear idea that the approach that you are proposing will not work? Or saying the other way around, it's what are the characteristics of the systems that are feasible to apply this proposal?
Yes. So
yeah, go ahead, Tim Hao.
yeah. So one guy like our algorithm make some assumption about the test program, and it has to be deterministic. So given a same set of configuration, it would reach the same location. So our algorithm would not work with like undeterministic programs like randomized algorithms.
Okay, so I was assuming when I read the paper that, of course, I mean, you need to have the test suites available in order to apply this approach. And of course, the systems should have the characteristics that they have to have certain number of configurations. I mean, I don't know if you have an amount, more or less, of these configurations that need to exist in order that the approach is worth to be applied.
So I think right now we make that assumption, and all of our algorithms and designs are based on the assumption that it will be deterministic programs. But I think in the chat window, Tim mentioned about using.
Yes, I was about to mention that we have a question from the audience. Tim Menzies, Professor Tim Menzies, says, any advantage to using random forest, generate multiple candidates with some variability in the scores across the trees?
Yeah, so this is a good suggestion. We have not thought too much about that, but I think this is something we should consider. This is our first time trying, like machine learning classification algorithms, so we didn't have a chance to try too many other than the some of the main ones like C5. But yeah, Kim Hao, I think this is something that we should consider using random forest, and then based on frequency, like what is suggested here. And yeah.
Good. Another part of the question is assess solutions by their variance, not just by the accuracy. Can handle non-determinism?
Yeah, so it might work. If we try this method using random forest or some other classification techniques that deals with frequency instead of accuracy, then I think it should work. And yeah, it'll be an interesting following up work for this.
Good. Any other question from the audience? I mean, you are free to do their questions here in the chat. You know as well that if we run out of time for the question and answer sessions. Oh, okay, we have one question more here. For advantages for random forest, compare Flash from him. I mean, a paper from him in TCA, and Boca. And for your information, Flash is single tree, and Boca is better with random forest. So very good advice with references that you can base on in order to follow up with his first comment. I mean, and actually with the links to the suggestions. Thank you.
Sounds good. We'll definitely check these out. Yeah. So Boca is also part of this year XC, right? Yeah.
Oh, perfect. Probably you should attend to that session and to do questions in order to clarify more or less how to approach the suggestions. Thank you very much. Any other question from the audience? No, well, as I said, there will be a discussion room after this session, so you can continue with the discussion. There is here by Tim Menzies and other reference that you can base your work on. Then I would like to ask you, so what is next for you? I mean, now you are receiving a lot of feedback on what other things you can consider. But what you had in mind to continue with this approach?
Yes, so we are looking to apply the technique to a more broad domain, like for offering the activation pattern for deep neural network. And we will also like try some new heuristic to reduce the number of configuration used so that we can use it on like a more complex and large systems.
Perfect. We have other comment from Tim Menzies that he's an expert on this topic. You also look at the sequential model optimization?
No, we have not. But we definitely will look at that. Yeah.
Do you think you could?
Sorry,
I think if you think that it's feasible to look at this.
We don't know what it is, but we'll definitely look at that after this.
Okay. You for sure. I think you should discuss with Tim Menzies after this session, so he can provide you more further feedback about the approach. I mean, he's an expert on this. I mean, I'm more than sure that it will be so helpful for you. I don't know if Tim would like to do other questions or other people from the audience. Or if you want to elaborate a bit more on the suggestions that Tim is doing.
So I'm looking at the link that Tim sent on HyperOpt. So it is an algorithms that have three algorithms: random search, tree of paths, and estimator, and adaptive TPA. So we'll definitely check these out, because we are right now we just try classification tree, and so anything that can improve that we'll be very willing to try, or not random search.
Tim is giving a lot of feedback, so I'm more than sure that you are so lucky that having all this feedback, and for sure, as I say, you are invited to move when we finish in some minutes. I mean, there is another question here that we have time, so we can't read it. Is Van Tien and Nguyen, did you talk about feature interactions? If yes, what are the highest interaction numbers that you found in your experiments?
So Kim, do you want to answer this? What is the highest?
Yes, we have some time, less than a minute, but we can start the answer, let's say.
Yeah, I'm not sure, like, do you mean like the number of different interaction in one program? If so, then in our experiment, the most we found is, let me see, for the LS program, it has 193 interactions.
Good. So we are now running out of time. So I invite you and the audience that would like to discuss further this paper to go with you to the discussion room, and the rest of the audience that would like to watch the video and then the question and answer session for the next paper, let's meet afterwards.